The Big Bang Theory has lost some validity with the new information discovered by the James Webb Space Telescope. We just made a surprising discovery that is revolutionizing world physics. The recent image captured by this telescope has generated compelling arguments that have surprised experts, putting an end to much speculation. For years, scientists have relied on the Big Bang Theory as the cornerstone of cosmology, but this new evidence suggests that there might be gaps in our understanding of how the universe began. The telescope's most recent discovery is visually stunning and could transform our understanding of the universe. This isn't just about a single image, it's about what that image represents, a potential shift in the way we perceive the cosmos. The discussion among experts that this image has resolved centers on the perception of the cosmos, challenging long-held beliefs about its origins and evolution. The stunning image taken by the James Space Telescope challenges our understanding of the universe in ways that few could have predicted, forcing us to reconsider what we thought we knew. This finding addresses one of the main problems in astrophysics: the age of the universe and its rate of expansion. Scientists of different generations have been puzzled by this unsolved phenomenon and have carried out numerous studies in search of answers, yet the mystery has persisted until now. Cosmologists investigate how the world originated, how it works, how it has changed over time, and how it will end. These are the fundamental questions that drive the field of cosmology, a science that blends physics, astronomy, and philosophy to piece together the story of existence. In the last 100 years, great advances have been made in this field, from the development of general relativity by Einstein to the discovery of cosmic expansion by Edwin Hubble. The Big Bang Theory, more accurately known as the Big Bang Theory, is the most widely accepted theory in cosmology. It holds that the universe has been expanding for approximately 13.8 billion years, starting from an extremely hot and dense state. This theory has been the bedrock of our understanding, suggesting that everything we see today, stars, galaxies, planets, emerged from a single point of infinite density. The Hubble constant, which indicates the expansion rate of the universe, is used to measure its growth, providing a numerical value that helps us estimate how fast the universe is stretching apart. However, determining how to measure the Hubble constant is not straightforward, and this has been a source of contention among scientists for decades. There are two main methods: local measurements and measurements of the early universe, each offering a different perspective on the same cosmic phenomenon. In space, objects such as stars and Type I supernovae, which are used as standard candles because of their constant brightness, allow astronomers to measure how far away they are and thus calculate the Hubble constant. These celestial beacons are critical because their predictable luminosity provides a yardstick for cosmic distances. As the expansion of the universe varies in speed, scientists can calculate the Hubble constant by observing how these objects move away from us over time. One of the main approaches is the measurement of the early universe, which relies on a different kind of evidence. Scientists use readings of the cosmic microwave background radiation, CMB, discovered in the 1960s as the afterglow of the Big Bang. This microwave energy comes from when the universe was only 380,000 years old, a time when it had cooled enough for atoms to form and light to travel freely. Astronomers can determine the age of the universe and its expansion rate by measuring the tiny ripples of temperature and polarization emitted by the CMB. These ripples are like fingerprints of the early universe, offering clues about its initial conditions. However, there is a problem. These methods do not yield the same result. Local measurements, based on observations of nearby galaxies and supernovae, suggest that the universe is expanding faster than the CMB data indicate. This discrepancy, known as the Hubble Tension, has left scientists scratching their heads. Scientists have been hard at work trying to understand why the results differ. To unravel more mysteries of the universe, more studies are underway involving telescopes, satellites, and advanced computer simulations. The differences in measurement indicate that we do not yet know all the science, or that there are errors in one or both methodologies. It's possible that our instruments are missing something, or perhaps our theoretical models need refinement. But thanks to the James Webb Space Telescope, likely a reference to the James Webb Space Telescope, JWST, we can peer farther into the darkness of space than ever before, revealing elements, planets, and galaxies we never thought possible. Launched in 2021, this telescope has infrared capabilities that allow it to see through cosmic dust and capture light from the earliest stars and galaxies. Scientists hope the data found would help them calculate the Hubble constant with greater precision, resolving the tension between local and early universe measurements. But the first wave of data has revealed new things that don't line up with our expectations, throwing a wrench into the works. Could this information give us a new perspective on space? We may need to rethink what we know about how the universe works, a prospect that is both daunting and exhilarating. We might discover particles and forces never seen before, or find that the dark energy, an unknown force that accelerates the expansion of the universe, needs to be reconsidered. Dark energy, which makes up about 68% of the universe, remains one of the greatest enigmas in modern science. With each new discovery, our ideas about space have evolved, building on the foundation laid by previous generations of researchers. For example, the cosmic microwave background radiation, discovered in 1965 by Arno Penzias and Robert Wilson, was strong proof of the Big Bang theory. Before that, scientists thought the universe would last forever, growing at the same rate indefinitely, a concept known as the steady-state theory. However, new evidence showed this way was not the case, and the discovery of the CMB tipped the scales in favor of the Big Bang. In the late 1990s, when we discovered that the universe was constantly expanding at an accelerating rate, we also learned about dark energy and its impact on its expansion. This revelation came from observations of distant supernovae, which appeared dimmer than expected, suggesting that the universe's growth was speeding up rather than slowing down. Every time we discover something new, we check whether it fits with our previous knowledge and generate new ways of understanding the universe. If it were not for this iterative process, the problems we face in cosmology could lead us to find better ways to understand the universe. Although this problem is complex, it is also exciting because it drives us to develop better tools to explore space. Tools like the James Webb Space Telescope, which has already exceeded expectations. Scientists around the world are interested in this cosmological problem because everyone wants to know more about the universe, from its birth to its ultimate fate. Most importantly, this demonstrates how science is always evolving as we learn more about space, adapting to new evidence, and refining our theories. SA tension, likely a typo for SA tension, is another concept that goes hand in hand with Hubble tension and refers to how matter is distributed in space. We use this information to create a structure of the universe and see how it has changed over time. Some areas of space have many galaxies clustered together, while others do not, revealing a web-like pattern of cosmic structure. Scientists use different methods to determine the magnitude of this dispersion, known as the S8 parameter, which measures the clumpiness of matter. One possible way to address this is to look at how different densities of matter, such as galaxy clusters, bend light from distant galaxies. This phenomenon, known as gravitational lensing, allows us to see where the dark matter is, which does not emit light and is therefore undetectable by traditional means. Dark matter, making up about 27% of the universe, exerts gravitational influence without revealing itself directly. Scientists also analyze the cosmic microwave background, the CMB radiation, and afterglow from the Big Bang. This light has traveled for about 13.8 billion years, carrying information since the beginning of the universe. By studying the CMB, scientists can understand how the universe was full of irregularities when it formed, providing a snapshot of its infancy. However, there is a problem. This data does not match the large-scale irregularities observed in the current universe. The non-spherical distribution of gravity suggests that matter in the early universe was more uniform than what we see with gravitational lensing today. This suggests that there is something we are not considering in our interpretation, which brings us back to the idea of dark matter and how it works. According to Ray, perhaps a reference to cosmologist Adam Rees, he and his team were able to redefine their work thanks to the Webb Space Telescope, and wanted to find out if a possible error in the Hubble Space Telescope measurements could be the cause of this discrepancy. However, the JWST showed the same deviations, which is worrying because it implies the issue isn't with the instruments, but with our understanding. Somewhere between these two observations, there must be a fundamental flaw in our understanding of the universe, Rhee said in an interview with an astronomical magazine in the United States. Using the new space telescope has allowed us to look deeper into the universe through its sharp infrared view and study cosmic distances with ever more precision. Both dark matter and dark energy are enigmatic components that make up a significant part of the universe, but their nature remains elusive. While black holes have been the leading explanation for certain gravitational effects, there is growing interest in exploring how dark matter and dark energy could influence these cosmic phenomena.